Hello friends, today we are going to see how to find out the in-order predecessor of a node in a binary search tree. So let's see. This is the binary search tree and we want to find out the in-order predecessor of any given node in this binary search tree. Now we all know that it is very easy to find out the in-order predecessor if we know the in-order traversal of a binary tree. But if the binary search tree contains thousands of nodes, then just to find out the in-order predecessor of a single node, of only one node, it is not feasible to find out the in-order traversal by traversing thousands of nodes in that binary search tree. And that too just for finding out the in-order predecessor of a single node, of only one node. So we should have a mechanism which allows us to find out the in-order predecessor without finding out the in-order traversal of the binary tree. Okay, so suppose if you want to find out the in-order predecessor of 40 in this binary search tree. Now this case is the case 1. So it says if the node P, means if the node 40 for which we have to find out the in-order predecessor, if that node P has a left subtree, means if it has a left subtree, that means if it has a left child, then jump to that left child. You have to jump to that left child and go to the rightmost node in that subtree. So let's see how to do that. See, for 40, is there a left child? Yes, that means the left subtree is present, and that is this left subtree. Okay, so let's jump to the left child. So I jump to the left child. Now what it says, after you jump to that left child, then you go to the rightmost node. So you go to the rightmost node in that subtree. So we came to the left subtree. Now let's go to the rightmost node. So let's go to the right child of 35. Yes, we came to 36. But is this the rightmost node? No, because its right child is not null. So again let's go to that right child. Now is this the rightmost node? Yes, because its right child is null, means this is the rightmost node in this subtree. So this node, that is 37, is the in-order predecessor for 40. Okay, let's verify our answer. So this in-order traversal, I have written it for verification. Whatever answers we are going to find out, we will verify in this in-order traversal. So let's see. See, for 40, what is the in-order processor? 37. So yes, our answer is correct. The in-order predecessor by our mechanism is correct, because in in-order traversal also the node which is previous to 40 is 37. Okay, now what is the meaning of this? See, as you all know, the in-order traversal of a binary search tree is a sorted order of the values in that binary search tree. Means it is the sorted order of this binary search tree that is written here. Now obviously if we want to find out the in-order predecessor of a node, then that means we have to find out the node which is previous to the given node. Means here we want to find out the in-order predecessor of 40. So inside the in-order traversal we will go to the previous node of 40. Means in the left subtree, see, the left subtree of 40 is this, the nodes before 40 in the sorted order. In this left subtree, 37 is the maximum value. See, whatever the values are present before 40, 37 is the maximum value among them. That means, see, for 40 we go to the left child, means we go to the left subtree, because we want a value less than 40. Okay, but in that left subtree the value which is maximum, that will be the rightmost value, because the property of binary search tree is that the right side of any node contains a value which is greater. Okay, so the right side contains the greater value and the left side contains the smaller value than that node. That is the property of BST. So that is why the rightmost node in this left subtree of 40 will contain the maximum value for that subtree. So that is the meaning of in-order predecessor. So let's look at the code now. So this is the code. See here, first we check if p points left is not equal to null. That means we check whether the left subtree is present or not. Means for p we check whether the left child is present or not. So if it is present, then we go inside the if condition. Now we jump to the left child. So that is written here. See, from p we jump to the left child, means temp will point to the left child of p. Okay, so this is that jump. Okay, now while temp points right is not equal to null, means we have to go to the right child of each node till we get null. Okay, and when the right child of the node is null, we have to stop. That is written here. See, temp equal to temp points right. So let's go. See, we went to the right. Now temp points here. Now temp points right is null. No, it is not null. So we again go to the right. So temp now points here. Okay, now temp points right is null. Yes, it is null. So we stop here and we come outside this while loop. Okay, when we come outside this while loop, we have to print that temp. Means we have to print the data of this node. Okay, that is 37. So in this way, the in-order predecessor of 40 is 37. Let's take another example. Suppose I want to find out the in-order predecessor for 90. So this is p now. Okay, so see here, first jump to the left child. Okay, so we have jumped to the left child. Now this is temp. Now go to the right till we get null. So this is the first right, then this is the second right, third right, but for this node the right side is null. So we stop here. We don't go to the right because that is null. So we stop here and we conclude this 87 as the predecessor for 90. So let's verify our answer here. Yes, 87 is the predecessor of 90. So our answer is correct. By our mechanism we have found out the correct answer. Now let's find out the in-order predecessor for the root itself. Okay, now let's jump to the left and go to the right till we get null. See, for 45 the right is null, so we don't go to the right, we just stop here. We stop here. That means 45 is the predecessor of 50. Okay, let's check. Yes, 45 is the in-order predecessor of 50. So this is the way we find out in-order predecessor for case 1. So let's look at the second case now. So the second case says that if the node P, means this is the node for which we have to find out the in-order predecessor, if that node P does not have left subtree. That means if that node does not have a left child. So suppose you want to find out the in-order predecessor for 79. Okay, now see, 79 does not have a left child, so we cannot go to the left subtree now. So what should we do? See, it is given here, search that node from the root and the node from where we take the last right turn is the answer. So I will tell you what it means. Okay, so the first thing is that you have to search that node from the root. See, this is P. Okay, so let's search this node inside this binary search tree. Okay, so let S point to the root. Now what we want to search? 79. So 79 is greater than 50. So let's go to the right side. Now S comes here. See, 90 is equal to 79? No, it is not equal to 79. So whether 79 is greater than or less than 90, it is less than 90. So let's go to the left side. You must be knowing how to search an element in binary search tree. So I am just following that procedure. Now 79 is greater than 78. So let's go to the right side. Okay. Now 79 not equal to 82. Actually it is less than 82. So let's go to the left side. Then again 79 is less than 81. So let's go to the left side. See here. Now 79 is equal to 79. That means we have found out the node 79. Okay. See, this is the search path of 79. In this search path, what is the last right turn? Okay. What it says in this search path, where is the last right? Okay. See here. This is the first right movement, means the first time we went to the right child. Okay, see, this is the left, this is the second right turn, means second time we went to the right child. Okay, then again left. Okay, so these are the two right turns we have taken in this search traversal. Okay, now the node from where we take the last right turn, means let's check what is the last right. See, this is the last right, this second right is the last right, because after this right we have never taken a right turn. So this is the last right. Okay, now from which node we have taken this right turn, means for which node we have gone to the right child. See, for 78 we have gone to the right child of 78, means 78 is the node from where we have taken that right turn. That means 78 is the in-order predecessor of 79. See, 78 is the answer. It is the in-order predecessor of 79. Let's check our answer. See here, it is 79. Yes, 78 is the in-order predecessor of 79. So this is the procedure. Let's see the code. See here, this is the simple searching mechanism. So we will see the code with some other example. So let's find out the in-order predecessor for 37. Okay, now let's see. While P points data is not equal to S points data. See, at first S will be at the root. Now see, now the search number is 37. 37 is not equal to 50. So let's go inside. This condition is satisfied. Let's go inside. If P points data is greater than S points data. See whether 37 is greater than 50. No, it is not. So we go in else. Okay. So we take the left turn because 37 is less than 50. So we take the left turn. Okay. Then whether 37 is greater than 16 or less than 16, it is greater than 16. So we take the right turn. See here, this condition is satisfied. P points data, that is 37, is greater than 16 for this node. For this node, this condition is satisfied. We are in a while loop. Okay. Now after this condition satisfies, we store the node from where we have taken the right turn. See, in this if condition we take the right turn. So we store the node from where we have taken the right turn. So we store this node. Store pointer is pointing to 16 because from there we have taken the right turn. So we remember that. So this is the right turn. Again in the while loop, check whether 37 is greater than or less than this node, that is 40. It is less than 40. 37 is less than 40. So we took the left turn. Now for 35, check whether 37 is greater than 35. Yes, it is. Now as we have taken the right turn, now we store that node. Okay, so this store pointer now points to the 35 because from there we have taken the right turn. Okay, now again in the while loop, check whether 37 is greater than or less than 36. It is greater than 36. So we took the right turn. So now again store will point to 36. See, from where we took the right turn, from each right turn for each node, we make our store pointer go and point to that node from where we take that right turn. So the last time store pointer is pointing to 36 because that is the last right, and now 37 is equal to 37. Now where is the last right? See, this is the first, this is the second, this is the third. So this is the last right, and from 36 we have taken that last right turn. So 36 is the in order predecessor for 37. So let's check. Yes, it is the in order predecessor. Let's check the in order predecessor for this node, that is 5. Okay, see here. Let's search this node 5 in this binary search tree. See, 5 is less than 50, so let's take a left. Now 5 is less than 16, let's take a left. 5 is less than 14, let's take a left. 5 is less than 10, let's take a left. And 5 is equal to 5. So we stop here. Now let's see, we have never taken the right turn in this path. There is no right turn. Nowhere we went to the right child. So that means there is no in order predecessor for 5. In order predecessor for 5 is not present. In order predecessor is not present. Okay, see here, for 5 in order predecessor is not present because 5 is the first node in this sorted order. So in this way this mechanism works. Now is the time to see why this mechanism works. What is the reason behind this procedure? Let's see that. So to verify this mechanism, we have to go in reverse. See, when we want to find out the in order predecessor for 79, what does that mean? It means that you have to find out a node which is immediately previous to 79, means immediately before 79. Okay, now as 81 is the left ancestor of 79. See, what is the meaning of left ancestor? The meaning is, if 79 is the left child of 81, that means 81 is the left ancestor of 79. That is the term I am using here. So as 81 is the left ancestor of 79, that means 81 is greater than 79 because 79 is the left child of 81. So 79 is smaller than 81. Okay, so 81 is greater. Because 81 is greater than 79, it cannot be the in order predecessor because in order predecessor is always less than that node. Okay, so it cannot be. So again let's go to the left ancestor. So again let's go to the ancestor. But for 81 also, its ancestor is the left ancestor. Okay, that means again 82 is greater than 79. Left ancestor means what? The node here this node value is greater than all the branches in the left subtree. As 82 is the left ancestor of all these nodes, 82 is greater than all these nodes, means 79 also. So as 82 is greater than 79, it cannot be the in-order predecessor. So let's go to the ancestor of 82. Yes, now this is the right ancestor. Right ancestor means 82 is the right child of 78. That is why 78 is the right ancestor of 82. So the first time when we find out a node which is lesser or which has the less value in this path, that node is the in-order predecessor, because we want a value which is immediately previous to our node, that is 79, which is immediately before. Okay, means the first lesser value. The first lesser value is 78. Now in this way we have reached to the in-order predecessor. But there is a big problem, because see, you cannot go reverse in this linked list. You cannot go reverse, because in the structure of the node of binary search tree, in the structure there is only a left pointer and right pointer. There is no parent pointer. Parent pointer is not present here. So how can we go back? We cannot do that. So we implement an idea. What we do? We search that node from the root. Means we find out the path to that node from the root. Okay. In reverse, the first right means if we go straight, it is the last right. Okay, in reverse, if it is the first right, then in straight path it is the last right. Okay, so that is the idea we have implemented here. We are finding out the last right, and the node from where we take that last right is the in-order predecessor. So that is the reason behind this mechanism. Everywhere on internet they will tell you the mechanism, but you will never know the reason from them. So this is the reason why we implement this strategy. Hey friends, please subscribe to my channel, as I post algorithm videos every day. And if you want a video on any particular topic, then please mention in the comment below. Thank you.